I want to introduce you to a couple of more advanced counting techniques, but first let's review what we know so far. A lot of counting is really just organizing the information that we have in front of us. And one of the ways that I like to organize this information is by just simply using slots, right? I draw the four choices that I have to make, and then I ask how many ways can I do the first one, and it's four. How many ways the second one? Let's say three, and then two, and then one. And then the answer is 4 times 3 times 2 times 1 does 4 factorial, right? That's the way that I could order four things along a wall. Now, you have to be careful because you need to keep track of things like, is repetition allowed or is repetition not allowed, right? So when you do 4, 3, 2, 1, you're assuming that repetition is not allowed. So after you pick something and put it in the first slot, then you can't pick it again for the second slot. That's why it goes down to 3. On the other hand, if you can reuse it, then it stays at 4, and you end up with 4 times 4 times 4 times 4. Okay, so that's one thing to keep in mind. The other thing to keep in mind is about ordering, right? Do we actually care whether we choose A, B, C or B, A, C, right? And are those different or are those the same principle? When we're counting with the slots and we put 4, 3, 2, 1, right? Then we're actually implicitly counting ordering. And the reason for that is that I can choose A, and then I can do B, C, and D for the second slot, right? So I get A and then something else. But I could have also chosen B on the first slot. That's why it's 4, right? So I could have chosen B, and then I can choose, well, A, C, or D for the second slot, right? So again, it's just 3. But now I could have gone A, B, or B, A, right? So that's counting different orderings. So to take care of that, what we do is we divide by the total number of ways to rearrange however many things. Now in this case, I have 5, 4, okay? So this is basically 2 out of 4, okay? And then this one here is 3 out of 6, right? So I have 6, 5, 4. And that's why I'm dividing by 2 factorial, because when I have two things, I can rearrange them in 2 factorial ways. And then times 3 factorials, because when I have those 3 things, then I can rearrange those in 3 factorial ways, right? So that's how I handle repetitions. That's how I handle ordering. And this kind of technique works really, really well for almost all problems, right? Now, the one thing that we run into one time, okay, just one time, but it does happen, is we sometimes actually have to completely break apart the outcomes and use the sum principle. So in this case, we have 5, 4, 3 divided by 3 factorial. That's because I picked 3 different things, okay? And then I have 5, 1, and 4 divided by 1 factorial. And what I've done there is I picked 2 things and then 1 thing, right? So we did it with the ice cream scoop. So, this is a way of saying, oh, I got 2 different flavors. So once I pick the first flavor, 5, then I have to pick that same flavor the second time. That's why we have a 1 here, okay? And the reason that I'm not dividing by 2 factorial is that if I picked 2 vanillas and 1 cherry, well, that's different than 2 cherries and 1 vanilla, which means that the ordering actually, well, it does matter, right? So because I can tell those 2 outcomes apart, okay? And then finally, there's the, oh, but I only chose 1 flavor, right? So I would pick cherry and then cherry and cherry, right? So that's why we have 1 and 1 here. And again, we're not dividing by any ordering because once I pick the flavor, it doesn't matter, right? It's just the 1. So in this case, what we had to do was break everything up and then add them together, okay? So that's everything that we've done. I mean, those are the techniques that we've used, and it's very effective, okay? Now let's look at some other ideas, right? Here's a problem that's actually really difficult to do using those techniques, right? And what we have is we have 3 women and 7 men, and we're going to arrange them in a wall, and then there's some kind of rule that says that 2 women cannot stand next to each other. Okay, so this is the kind of thing that people in protocol worry about, right? Is how to set up some people around a table or something, and then there's some kind of constraint. Okay, so how many ways can we do that? Okay, now the problem is that where I can put the 3 women varies as soon as I put one of them, right? So I can't simply say, oh, the third position I have these many ways of choosing, because that depends on whether I can select a man or a woman for a spot, which depends on whether I selected a man or a woman for spot 2 and spot 4. So that's why this is hard. So there's a trick that's actually pretty famous and pretty cool for this, and it's called the stars and bars approach. Okay, and you want to start thinking stars and bars when we're arranging, two kinds of things. Okay, so the stars and the bars, and here's how we're going to do it. We're going to keep the rule that says that no two bars can be adjacent to each other. Okay, and then the rest of it doesn't matter. Okay, so here's our plan. We have some stars, right, that we're putting together. Let's say that I have 4 stars. Okay, and so this is 4 men, right, and I place them, right, and now I want to put 2 women among them. Okay, but the rule is that I can't have 2 women next to each other. Okay, so where can I put a woman? Well, I can go there, 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 and there. So you see there's 5 places where I could put one of the women, right? And now what I have to do is choose 2 out of those 5 slots. So there's one possibility. Here's another possibility. I can put one here and one there, and so on, right? And now you see that the solution ends up being just 5 choose 2, right? So it's actually a similar problem to what we did before once you recognize it. And these stars and bars is a good way of organizing that kind of information. Okay. Now let's follow this a little bit more closely. Okay. So so that's our plan, right? That's how we're going to put the 3 women among the 7 men. But we do need to think about some kind of corner cases and see if that's allowed. You see right here what we have is 8 choose 3. And why 8 choose 3? Well, since I have 7 men, then I have 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Okay, and 3 of those I'm going to put a woman in. Okay, now is that really what I want? Because I could, for example, say, well, I put 7 men, against the wall, right? Maybe it actually matters who's the leftmost one and who's the rightmost one and so on. Maybe the ordering matters. So to fix that, what I can do is just simply multiply by 7 factorial, right? Because once I figured out where the men can go, now I can rearrange those at will. And of course the same goes for the women. So I also have to multiply by 3 factorial because I can be moving them around. Okay. All right. So that works really well, right? There are still some issues that you might want to consider. For example, maybe there's a kind of protocol, right, that would say that the women can't be on the ends. Okay, why? I don't know, right? Let's say some protocol person makes up that rule. Well, in that case, then I wouldn't have 8. I would only have 6 slots, right? So it would be 6 choose 3, right? That's the kind of thing that you have to pay attention when you're actually setting up the solution to these problems, right? Because it just depends on specifically what people want to count. All right. Now let's try something else. Let's say that I have 20 gifts, okay, that I'm going to give to 10 students, right? Maybe these are incoming students. I want to encourage them to come to UW. So I have 20 things and I have 10 things that I want to put in between. So again, I'm going to use this stars and bars approach, right? And so what I have is the stars are the gifts, okay? And I have to break them up in many different ways. And the bars give me a way of breaking them up, right? In fact, think of the bars as setting up little areas or boxes. And so the things go inside that, right? So I have 20 stars and 9 bars, okay? I have 10 students. Why do I have 9 bars? Well, the idea is that if I have 9 bars, then I've explicitly divided the whole space into 10 regions, right? 1 for each student. So that works, okay? Now, why not exactly 10? That's kind of a classic fence posting problem, right? If I make it exactly 10, then I actually have 11 slots that appear, okay? Maybe I should have gone to 11. Well, you see exactly the issues here. I mean, that's why we chose 9. Although there are some subtleties, as you would expect. Okay. All right. So let's see. We have how many different places to put in those 9 stars? Well, there's 21, right? And why 21? I have 20 stars, right? So I can go in between. There's 19 spots in between, and then there's the 2 ends. That is 21. Okay. But here's a problem with that approach, right? I have, let's say I only have 3, 3 of the stars here, okay? And then I would have 4 slots where I could put in bars. Well, if I do them like this, okay, then what ends up happening is that this poor student got absolutely nothing. This student here got absolutely nothing, right? But you see, the student that's number 2 is always going to get something. There's no way for that not to happen. So it's really inconvenient to be the first or the last. Okay, so that clearly doesn't seem fair. So I might simply say that these slots are not allowed. Okay, and if I do that, then I don't have 20 plus 1 or 21. I only have 19. So it's 19 choose 9. Those are the places that I can put my dividers. Okay, or I could also say, look, let's make it 21 choose 29 choose 9. And now what I'm actually allowing is to have kind of areas in between that I can have 2 consecutive bars, and that means that well, whatever student went in that slot doesn't get anything, right? So I could do that too, right? It's just a matter of deciding what it is that I want to count, and then arranging the stars and bars appropriately. Okay, so let's say that the answer is 19 choose 9. Everybody gets at least 1 souvenir. I think that's fair. That's what I want to go with. Okay. Now what about the student ordering? Does that matter? Okay. Well, I have 10 students and I'm creating 10 slots. Each slot has presents, right? Well, it doesn't really matter what the ordering is in a certain sense, right? Because I will simply choose. I will choose an ordering. This is the first student, this is the second student, this is the third student, right? And then I can assign, gifts to the first student, to the second student, to the third student in a fair manner. So it's all good, right? So in a certain sense, the ordering does matter, right? Because the ordering with the students is important, but already taking care of it because we're simply saying first student, second student, third student, right? So any ordering is good, right? We've already accounted for it, okay? Now, what if the souvenirs are indistinguishable? Okay, so if I can't tell them apart, then we're done, because the only thing that matters is how many does each student get, right? But what if they're not indistinguishable? What if some of those are shirts and some of those are cups? Okay, well, then what we're going to need to do is kind of multiply by the possible ways of reordering the gifts, right? So let's say that we start out and there's 20 totally different gifts, right? So I could say the first student gets 3 of them, right? Okay, which 3? Then I need to consider all ways of ordering those 20 different things, and that's why I would multiply by 20 factorial, right? But if there's only 2 groups of things that are independent, then I need to multiply by something like 5 factorial times 15 factorial, right? So that I get the right number, right? And that becomes accounted, right? I mean, I might be able to tell this 5 need reordering, but not between the 5 and the 15. Okay, so okay, so that's a new strategy. That's the stars and bars.